Welcome back. In this video lecture, we will see the last very important property of the Laplace transform, which is the time shift, and we will apply it to compute the Laplace transform of piecewise functions. So let's start with this property. It is called the time shift, and it says the following. Let's assume that we have a function ft that is admissible. So that means that it has a Laplace transform that we will call it capital F of S. Then this property says that if we apply a translation in time and we multiply by UA, I will explain this in a few seconds, the meaning of this. Then what happens in the frequency domain is that the Laplace transform gets multiplied by the exponential of minus SA. So you see here the main differences. I had ft here, I switched to ft minus a and multiply by the step function. And what happened in the frequency domain is that the Laplace transform get multiplied by the exponential. That's the property called time shift. The meaning of multiplying by UA is pretty simple. Remember that UA is a function that is 0 up to a, and then its value switches to 1. That's UA. So whenever I multiply a function by UAT, what I'm doing is just making it to be 0 before a, because I'm multiplying by a. So only the function from a and up to infinity remains with values different from 0. Now, let's see how this property can be used to compute the Laplace transform of piecewise functions like this one. Here, we have a piecewise function. It is a function that is given in 3 different parts. First part goes from 0 to 1, and it's a parabola. So it looks like this, t squared. Remember that here, this axis is the t-axis. So this is t squared. Then between 1 and 2 is a line with a slope minus 1, so decreasing, okay? And from 2 higher values of t, the value is just 0 forever. Now, we want to compute the Laplace transform of this function. The way to do that, the way to compute the Laplace transform of this type of functions is first rewrite f of t as a linear combination of Heaviside functions. So this first step is what we covered in the previous video lecture. Let me go back for a moment. In the previous video lecture, we saw that for any piecewise function, like this one, we can rewrite it in such a way that is given in a single line, and it's just a linear combination of Heaviside functions. So that's what we will use now in order to rewrite our function, okay? So let's use this here. Now, in our case, we could think that t squared starts from minus infinity to 1, okay? It would be the same case because the Laplace transform, it's only defined from 0 to infinity. So there's no importance on the behavior of the function before 0 that will not be taken into account by the Laplace transform. So if it's easier for you, you can think, as this is a 0, okay, you can think that the function is defined like this. For t smaller or equal than 1, this is t squared. So this would be our first case that we have here. Okay, this case. So this is equal to the first case we had. This case here is similar to this second case we had. And finally, the third case is also this type of case where t is bigger than a given number. That's what happens here. So that means that we can apply exactly the same where t squared is f1, 2 minus t is f2, and 0 is f3. Of course, this is equal to a, and this is equal to b. So, in particular, our f of t function can be written as, now f1 is t squared times 1 minus ua, but a is 1, plus f2, which is 2 minus t, times ua, a is 1, minus ub, b is 2, plus f3, but f3 is 0, so that would be 0 times whatever is going to be 0. So I'm not going to write it down as it is 0. So what we have here is linear combination of Heaviside functions u1 and u2. So let me write it putting together the terms that are constant and they are not multiply, the terms that don't multiply u1 or u2. So for example, t squared, that's already used. And that's it. Then we have the terms that are multiplying u1. Basically, we have minus t squared. That's already used. And here we have 2 minus t. That is also multiplying u1. And finally, the terms with u2. The terms that multiply u2, as we have this minus here, is t minus 2. Okay, 2 minus t, but with this minus, they switch. Okay, so now we somehow completed the first step, which is to rewrite f of t as a linear combination of Heaviside functions. Now we completed this step. Now f of t is written not as a piecewise function with different cases, but now it is written as a linear combination of Heaviside functions. Now, we can use the property that we saw at the beginning of the video lecture in order to compute the Laplace transform. So the next step is to compute the Laplace transform of f of t, which now simplifies to compute the Laplace transform of, using linearity, t squared, the Laplace transform of u1 times minus t squared minus t plus 2, I reordered a little bit here, plus the Laplace transform of u2 times t minus 2. Okay? This Laplace transform is very easy. You can find it in the table of Laplace transforms, and you will see it is 2 factorial, so that's 2 divided s to the power n plus 1, which is 3. Okay, what we are using here is the fact that t to the power n has as its Laplace transform and factorial divided s to the power n plus 1. So this part is pretty easy. What about the other parts? I will start with this one because it's a little bit easier, okay? What about this? Okay, this Laplace transform is the Laplace transform of u2t. Who is u2t? Another way to write that is ut minus 2. This is very, very important. You should always remember that writing this u2t means making a translation of 2 to the function u, okay? So what we are saying here is that if I have my step at point 2, so the function is 0 here, and then it switches to 1, okay? This function u2 is exactly the same as applying to the function ut, which has the step at point 0 at the origin. This is exactly the same as applying to the step function at the origin a translation of 2 to the right. Yeah, I'm somehow pushing this step to this position. Okay, so in that way, if we use this other notation, it's really much simpler to compute the Laplace transform that we will do just now by using the property we saw at the beginning of this video lecture. Remember this property here, okay? So I will write it down there. Maybe it's easier if I copy it, so you will see it like it looks here. So we will use this property at this step. Okay? So this property is telling me that if I have f of t minus 2 times u t minus a, or this could be also written as uat, okay? Then its Laplace transform is just multiply by the exponential. Oh, sorry, I'm using here a. The value of a, I'm assuming, is 2. Then I get minus 2s times fs. Now, that's exactly what I have here, okay? You can see that this function here is exactly what I have here, okay? But here, t minus 2 corresponds to ft minus 2, okay? Now, if ft minus 2 is equal to t minus 2, who is f of t? You can think this as t tilde, like change of variables. So of course, this is t. Okay? So the function f of s here, that's very important, is the Laplace transform of f of t. So that's why I need to know who is f of t, because the Laplace transform of this function, which is this function, its Laplace transform is going to be the exponential of minus 2s times the Laplace transform fs, which is the Laplace transform of ft. So the Laplace transform of t. Oh, the Laplace transform of t is 1 over s squared. So the Laplace transform of this term is this one. Okay? This was pretty simple to apply because this function t minus 2 is pretty easy to do this change of variables and to know who is f of t. So if f of t minus 2 is t minus 2, ft is just t. But we will see it can be a little bit harder. For example, with this case here. So now we will do this last case, okay? we will try to compute now the Laplace transform of this other term, u1t minus t squared minus t plus 2. Now, the problem here is that if I want to use this property here, I need to have my u function, my Heaviside function, multiplying f of t minus a. And this doesn't look like t minus 1, which should be. So I need to rewrite it in such a way it appears t minus 1. So our work here is to rewrite u t minus 1 that multiplies minus t squared minus t plus 2. I would like this to be very easy to see which function it is when I'm applying this change of variables, but now it's very difficult. So I need to rewrite this in such a way that it appears this t minus 1. So I will do that. How can we do that? Let's do that. Whenever I see a t, I will write t minus 1 plus 1. Do you follow what I'm doing? So I have this t here. I'm changing it to t minus 1 plus 1. Okay, I will proceed with the next t. I will change it to t squared. Then next t minus 1 plus 1. And then I also have done, I have replaced this t by t minus 1 plus 1. And I will continue with the plus 2. Now, what's the purpose of this? I will try to keep this t minus 1 together. So I will do all the algebraic calculations, but always keeping the t minus 1 together. Okay? So here, for example, t minus 1 squared plus 2 times t minus 1 times 1 plus 1 minus t minus 1. Now this minus with this 1 is a minus 1 and plus 2. So I will continue. And putting things together, we get t minus 1 squared. Okay, that's already used. Then I have minus 2 times t minus 1 and minus t minus 1 again. So that's minus 3 times t minus 1. And then we have a minus 1 here. Ooh. And then we have, sorry. Okay. And then we have minus 1 here. And minus 1, that's minus 2, plus 2 is 0. Yeah. So what I have at the end is that I could rewrite this polynomial in this other way. It's the same polynomial. But now it's really easy to go from, if this is f of t minus a, and it looks like this, then it's very easy to do this change of variables and guess who is f of t. Well, f of t is minus t squared minus 3 times t. So now it's going to be pretty easy to apply here this property. Okay, so now we will apply here this property. Now, who is f of t minus a? This is f of t minus 1. This is u of t minus 1. which you can also call u1t, okay? It's already written here, u1t. And this function, f of t minus 1, can also be written like this. And that's what helped us to know who is ft. Ft is this function. Now, I have exactly what I want here. This f of t minus a uat is this function ut minus 1 times f of t minus 1. So I'm using a equal to 1 for this specific case. And its Laplace transform is going to be the exponential of minus s, because a is equal to 1, so this a is equal to 1, times f of s. But very careful, who is f of s? F of s is the Laplace transform of f of t, this function, okay? So who is f of s? The Laplace transform of this is minus, now remember, at the table of Laplace transforms, this one for polynomials. So in this specific case, for t squared, we have 2 factorial over s to the power 3 minus 3 times 1 over s, which is the Laplace transform of t. So this is what we will write here. Minus 2 divided s to the power 3 minus 3 times divided s. So let's try to sum up. This is the last term needed to compute. This is the Laplace transform of this second term that was a little bit harder, okay? So the Laplace transform we wanted to compute is the Laplace transform of t squared, which is 2 divided s to the power 3. Let me sum up here. Maybe we can do a little bit of place here. So the Laplace transform of f of t is this first term, which is 2 divided s to the power 3, plus this other term that was a little bit harder to compute, which is this term here. So let's copy it. E to the minus s times minus 2 s to the power 3 minus 3 times divided s, plus this last term that we computed first because it was a little bit easier, which was equal to this. So let's write that part. E to the minus 2s, e to the minus 2s times 1 over s squared. So this is the final, So this is the final solution of the problem we wanted to solve. This is the Laplace transform of the piecewise function we wanted to compute its inverse Laplace transform. So it's Laplace transform as we had in this problem here. This is a very important property, this one that we saw today, and it is used a lot. This property is used a lot to solve initial value problems or integral differential equations where piecewise functions appear. Whenever you have a piecewise function, almost always you will need to apply this property, the time shift property, as we saw today. So that's it. Thank you very much. Bye-bye.